Whether it's one of those giant metal boxes you see on a power pole or that little black brick that charges your phone, you're interacting with transformers pretty much every single day. They are the quiet, unsung heroes of our electrical world. Seriously, without them, modern life would just grind to a halt. So let's dive in and see exactly how this incredible and incredibly important device actually works. Really think about that for a second. Power plants can be hundreds, sometimes thousands of miles away from your house. Yet the electricity arrives at your outlet perfectly ready for your laptop or your TV. How is that possible? Well, the answer lies in solving a really fundamental electrical dilemma.
And this is what we're talking about. You could call it electricity's great dilemma. It's this classic tug of war between the need to be super efficient over long distances and the need to be super safe when that power gets into our homes.
And this right here is the heart of the problem. To send power across the country without losing most of it, you need incredibly high voltage. Think of voltage like water pressure. You need that high pressure to push the energy a long way with very little getting lost as heat. But you can imagine that same extreme voltage would be, well, catastrophic coming out of your wall. On the flip side, the low, safe voltage that's perfect for your home would just fizzle out over a long journey, losing almost all of its energy. So we need a way to have it both ways.
And this is its job. The transformer is that perfect middleman. It's the device that lets us switch between that high voltage for the long haul and low voltage for safe use, exactly when we need to.
So how does it pull this off? You might be picturing some complex, whirring machine, but the true genius of the transformer is its beautiful, elegant simplicity. So let's take a look inside the black box.
It really boils down to just these three simple parts. First, you've got a core, usually made of iron, which is fantastic at directing magnetic fields. Then, you have two completely separate coils of wire wrapped around that core. A primary coil, where the electricity comes in, and a secondary coil, where the new transformed electricity goes out. And that's it. No moving parts, nothing complicated, just wire and iron.
But hold on. If the coils aren't touching, how on earth does the energy get from one to the other? This, my friends, is where the physics gets really cool. It all happens through a principle called electromagnetic induction, first figured out by the brilliant Michael Faraday.
Okay, so the absolute key here is that our grid uses alternating current, or AC. That means the electricity is constantly flipping its direction. Now, as this AC flows into that first primary coil, it generates a magnetic field that is also constantly changing, growing, shrinking, and flipping. The iron core then grabs this pulsating magnetic field and channels it over to the secondary coil. And here is the magic. As that changing magnetic field sweeps through that second coil, it actually induces a brand new electrical current in it. The energy literally jumps the gap, no physical connection needed.
Okay, so we can move power between coils. But how do we control if the voltage goes up or down? Well, the answer is so simple it's almost funny. You just change how many times you loop the wire around the core. This is called the turns ratio.
This table lays it out perfectly. If you want to increase the voltage, to get it ready for that long trip on the power grid's highway, you use a step-up transformer. It just has more wire turns on the output coil than the input coil. That's what you'll find right next to power plants. Then, to decrease the voltage for safe use in your neighborhood, you use a step-down transformer, which has fewer turns on the output side. Those are the ones you see on the utility poles right outside your house.
And it all boils down to this really simple, beautiful equation. The ratio of the voltages between the two coils is exactly the same as the ratio of the number of wire turns in those coils. That's it. By controlling one simple physical thing, how many times you wrap a wire, you get precise, predictable control over the voltage. It's incredible.
Now, this is a super important point. A transformer isn't some magical energy machine. You can't get more power out than you put in. The law of conservation of power still applies. So what that means is, if you step the voltage up, the current has to go down, and if you step the voltage down, the current goes up. It's a trade-off, plain and simple.
So we've mentioned alternating current, or AC, a few times. And it turns out, for a transformer, it's not just a preference, it's a strict, non-negotiable requirement. Let's dig into why that is.
Remember the secret sauce for induction? A changing magnetic field, right? Well, alternating current, by its very nature, provides this. It's always fluctuating, always moving, and that creates the pulsing magnetic field we need. Direct current, or DC, on the other hand, is like a calm river. It's a flat, constant flow in one direction. Sure, it creates a magnetic field, but that field just sits there. completely static.
And a static magnetic field does absolutely nothing. No change, no induction. End of story. So not only would a transformer just fail to work with DC, but the primary coil would basically become a dead short, drawing a huge amount of current. It would overheat and probably burn itself out in a hurry. This is the fundamental reason our entire power grid is built on AC. The transformer demands it.
So when you put it all together, what do you have? You've got a device with no moving parts based on a simple and elegant principle of physics that solves an absolutely massive engineering challenge. It's the key that unlocks our ability to build huge, continent-spanning power grids that deliver energy safely and efficiently right where we need it.
So next time you plug in your phone, think about it. That little charging block is a tiny, miniature step-down transformer. It's taking the 120 or 230 volts from your wall and converting it down to the safe 5 volts your phone needs to charge. It's the exact same principle we've been talking about, just on a much smaller scale. It really is the unsung hero, working quietly on the power lines, in your home, and even